Cooking also involves a lot of phase transformations with denaturing of proteins. But we do need to, there are things that I would feel horrible about if you were not prepared going forward. And one of those is grain growth, and one of those is martensite. So we should talk about it. Okay, so the fudge seized. What does it mean when fudge seizes? I've never made fudge. It's one of those the few cooking things I've never done.
This one's just better if I explain it verbally. Otherwise, I'm going to be typing for 5 minutes. Basically, when you make fudge, you super saturate sugar into milk, and you have to be really careful not to get another sugar crystal in there. Otherwise, it'll start to crystallize and seize up. And that's exactly what happened to me. I had it all super saturated, and I went to start stirring it, and the whole thing started to crystallize, and it turned into a chocolate brick, essentially.
Ah, okay. It sounds wow, I should have asked you to write your paper on that. Okay, well, anyway, we talked about velocity and of the interface and the grain boundary mobility, right? The driving force is just the change in free energy. We have a net flux from one side of the interface from the other that's given by the Gibbs free energy curve. And of course, this change in energy from one side of the interface to the other is given by curvature of the grain boundary, which goes back to our good old friend Gibbs-Thompson, right? And so grain growth is generally called curvature-driven grain boundary migration. And because it's diffusional in nature, it should be no surprise to anyone that we have a growth velocity term that's exponential with respect to the activation energy, right? And so we can combine all this stuff together. And normally what we do is we express a velocity term in terms of the grain boundary mobility times the driving force divided by the molar volume, right? And so what we can do then, if we assume that the curvature, the curvature of our grains is related to the grain size distribution, we can relate an average curvature to an average grain size, and we can relate and come up with an expression for the average velocity. That's going to be our mobility times our surface energy divided by our average grain size times the geometric factor here, a fudge factor that's going to be about 1, right? And using this, we can figure out where our velocity essentially slows, right? And we can come up with a expression for our rate of change of our average grain size with respect to time, right? It's fairly qualitative, but it gets the right sort of general picture. We left off on Monday talking about solute drag and pinning. And so when we talked about diffusion and solid solutions, we said that solute many times will want to go to a grain boundary, right? It will segregate to grain boundaries because there's more free volume there. It's easier for atoms to fit in if there's a large size mismatch, or if atoms have a slightly different, the solute has a slightly different valence state than than the matrix. And the key idea here with respect to grain boundary migration is that if our solute is happy at the grain boundaries and unhappy in the bulk, that gives us an extra energy penalty that we need to overcome to move our boundary. So that means our boundary is not going to break away from the solute very easily. So that means that the rate of grain boundary migration is going to be determined by how fast our solute can diffuse, right? And so the solute diffusion becomes the rate limiting step, and this is called solute drag. And we can see this here. This is lead, and we can look at the grain boundary, in this case, the velocity, as a function of the concentration of tin in solution. And we see that it doesn't take a huge amount of tin, right? 0.6% weight percent. Oh, this is already in percent. So 0.006% or weight fraction of 6 times 10 to the minus 5 to give us 4 orders of magnitude in change of the grain boundary velocity, right? So this is a really important strategy for alloying. For those of you who take physical metallurgy class, either from me or Professor Fraser, whoever teaches it is teaching it in the future, we'll spend a lot of time talking about grain refiners. And there's 2 types of grain refiners: those that enhance recrystallization, right, meaning nucleation of new grains, and those that essentially prevent grain growth, right? That's 5441, right? So it's currently offered in the fall, so take it next fall. It'll probably be Professor Fraser teaching it again, because I'll be teaching this class again. Right, but a really good class for those who are interested in metals, and really useful for welders who are interested in learning about titanium and superalloys and aluminum. A lot of the focus is on non-ferrous alloys, right? Non-ferrous systems, right? So another thing we have to consider is that small particles are going to also slow down the growth of grains, right? The easy way to picture this is that if the surface energy of the, again, this is where I left off because I want to be really careful about this. It's a complicated enough phenomena that I don't want to speak in generalities, right? But if we think about this particle, right, we have a interface between the matrix and the particle, right? And if the grain boundary comes up to this particle, essentially we've eliminated that much interface from the grain boundary. And if this grain boundary is high energy, we're not going to break away. We're not going to want to break away. Okay. Now there's subtleties that come into play here based on the balance. And that was where I want to be careful, because I don't want to talk about that and confuse the issue. It's my, when I find something interesting, it's my tendency to talk about it a lot. I don't want to do that here, because I want to keep the picture simple for you guys. But essentially, we can, if we think about being able to eliminate some interfacial energy, it means that when the grain boundary is touching all these particles, it's in a lower energy state than when it's going through the matrix. So that's going to provide a resisting force, right? And it's fairly easy to show that this resisting force is going to have to do with the volume fraction of the particles and the radius of the particles, right? And the surface energy of our grain boundary, the grain boundary interfacial energy, right? And so this is known as Zener pinning, right? And it's a really important phenomena, okay? So generally, what's true for secondary phases is true for pores, okay? So this is, we're bringing it back to sintering here a little bit, right? So pores or voids can't enhance mobility. They can only leave it unaffected or reduce it, right? So that's why we said that in sintering, right, when we get into final stage sintering and we don't have pore channels along the grain boundaries anymore, we only have pores at the grain corners, we suddenly get a big spike in mobility, right? Because we have all these pores that are acting essentially as pinning sites of the grain boundaries that are now gone. So during the final stages of sintering, the pores are going to shrink and the mobility of our grain boundaries is going to increase, okay? Pores don't always shrink during sintering though, right? They can coarsen, just like secondary phase particles can. They can also grow by the same type of Oswald ripening mechanism that we talked about earlier, right? Small pores can essentially diffuse away and have large pores grow. There can also be evolving gas reactions. So pores are a bit of a complicated situation, okay? But if you just think of a pore as like being a secondary phase, I think you're pretty good. So the pinning force for Zener growth, for Zener pinning, either with particles or pores, is going to oppose the growth for new grains. Okay. When our grains are small, all of our boundary curvature is very large, and the pinning force is going to be relatively insignificant relative to the driving force for coarsening. Okay. But as our diameter increases, our curvature becomes smaller and smaller and smaller. And eventually, the driving force for curvature-driven flow is going to be too small to overcome the pinning force from the obstacles, right? So that means we're going to have a max grain size that's going to be related to the radius of our particle and the volume fraction of our particle, right? And this is a really useful rule of thumb, right? That our maximum average grain size is going to be 4/3 times R over F, our fraction, right? And we can see this is schematically, but the real experimental data looks like this. If we have a pure metal, right, our grain size keeps growing and growing and growing at a decreasing rate, right? It has a rate that's going to go by diffusion. So our grain diameter follows a parabolic growth rate, right? But when we have a particle dispersion, our growth rate is less. And eventually it hits a point where it just all grain growth ceases, right? Because of our particle dispersion, right? Really important in things like aluminum alloys, precipitation strength in aluminum alloys, right? So something to look forward to in the future. We can also have abnormal grain growth. Okay. And the causes for abnormal grain growth in both metals and ceramics are complicated. They're still not entirely clear, right? So this is more of a information. This is a phenomena that exists, but we're only going to talk about it in the most qualitative sense. Okay. But abnormal grain growth is, as you can see here, where we have a large number of grains that are all about the same size. And then we get one huge grain. And where on earth does this come from? And it happens in metals too. Here we see a fine grain structure throughout the whole sample, and then a couple very large grains, right? And so in metals, this can largely happen when we have a fine array of precipitates and a combination of strain, right? So we have dislocation energy, right? So we can, if we grow these grains, we can eliminate and create new crystal behind here. We can eliminate the stored energy of dislocations and the grain boundary energy here. And essentially, we just are at this right balance where everything isn't homogeneous, right? Our structure has enough heterogeneity in it that locally the driving force for growth is a little bit higher in some region, and the restraining force is just a little bit lower. And that can allow one grain to essentially break away. And then once it starts growing, it can eat up a neighboring area, right? It's a very incomplete story, right? But the science is still largely incomplete, right? And it's a very complicated phenomena. There are also cases where, like in the ceramic, you get a composition where you get a little bit of liquid, right? If we're near the eutectic, right, we can have thin liquid films that form due to a compositional heterogeneity that causes one grain to grow much larger, right? Similar things can happen in metals as well, right? There's multiple causes, multiple cases, right? I don't want to dwell on it. It's just one of these things you should be aware that it does happen. Okay, so that's it for grain growth and sintering. We're going to start our second to last topic, right? And that is twinning and martensite, right? And then we'll go back to crystallization in and diffusion in glasses and polymers to wrap everything up. So we'll start this today. We'll finish it up on Monday. Right. And so yeah, we're getting down to the end. Okay, so why do I have twinning and martensite here together? Because this martensite's a phase transformation, right? Twinning, this is a mechanical process. This is a deformation mode, right? It turns out that twinning and martensite have a lot in common, right? They actually have share a lot of features, and it's much easier to understand martensite if we talk a little bit about mechanical or deformation twinning first. Okay, so twinning, like slip, occurs as the result of applied stress. It involves a lattice reorientation, right? The martensite reaction is a phase transformation that has a large associated mechanical component with it. It's a shear transformation. Sometimes it has stress is influential in triggering the martensite transformation. Okay, but primarily it's a chemical driving force. It's the reduction of free energy between two phases. But the actual sort of atomistic mechanism are very closely related. Okay, there's analogous ways that twins and martensite crystals form. Okay, the atoms inside these crystalline volumes are realigned to form new crystal lattices. In twins, this realignment produces a lattice that has the original crystal structure, but with a new lattice orientation, right? We have a rotation of a large part of our lattice relative to something else, right? But we still maintain a cubic lattice. In martensite, we have a reorientation, but we also have a distortion of the lattice from one crystal structure to the other, right? But the mechanisms and the resulting microstructure ends up being quite similar, right? So here we see a high amount of deformation twinning in a TWIP steel. This is a twin-enhanced plasticity mechanism in certain steel compositions. And here we see martensite in low carbon steel, right? Martensite is not important only in metals. There's many ceramic and geological materials that have martensite transformations. Twinning is also an important deformation mechanism in geological materials, right? Dauphine twins in quartz and perovskite materials are important geological deformation mechanisms in the Earth's crust, right? So while it's easier to talk about these things in metals sometimes, right? Both twinning and martensite are really important for ceramics, right? Zirconium oxide is a very important technological material because it is the primary thermal barrier coating that's used in turbine engines, right? The blades are coated with a thin layer of zirconia because it has a very low thermal conductivity. So if we have active air cooling in our blades, we can have very high temperatures on the outside, and the thermal barrier coating acts as a layer of insulation, right? And allows the heat flow from the environment to the blade to be slow enough that the cooling in our turbine engine can actually remove the heat. And this can be effective enough that we can have operating temperatures inside a turbine engine that actually exceed the melting temperature of the blades, of the nickel superalloy in the blades, right? Because of this combination of active cooling and thermal barrier coating, right? The challenge in developing this technology was that zirconia undergoes a martensitic transformation. It transforms from cubic to monoclinic, right? So we've the active development in the 80s was the essentially the invention of what's called YSC, or yttrium stabilized zirconia, where you have zirconium oxide that is doped with yttrium to prevent that martensite transformation, that martensitic phase transformation. Okay, so exceptionally important in ceramic materials as well. I'm not aware of any polymer martensites, but there probably are. Okay, so what makes twinning and martensite different than everything we've talked about before is that they are diffusionless, right? They're sometimes referred to as military transformations, right? There is no long-range transport. There's not even short-range transport. It doesn't require local, long-range or local atomic jumps, okay? Much like marching is the most efficient way to move large numbers of people on foot, right? You can think of the lattice moving in a cooperative or homogeneous movement. Many atoms simultaneously change that results in a change in crystal structure. The movement of each individual atom is small, less than one atomic, normally less than one interatomic distance, right? So the amount that an atom moves during twinning or martensite is less than the atomic jumps that happen in a diffusional phase transformation. But because everything happens at once, it leads to large macroscopic changes, right? And that sort of takes a little bit of wrapping your head around. Compare that to, the diffusional transformation, which is often referred to as a civilian transformation, right? For those of you who took part in protests this summer and fall, right? You know that it's an uncoordinated movement of people, of atoms. There is a biased random walk, right? Not everyone in the crowd is moving at the same pace. Not everyone in the crowd is even moving in the same direction. Okay? So the kinetics of diffusional phase transformations tend to be slower. The kinetics of these diffusionless transformations are rapid, very, very fast, right? And this is a fundamental difference. Okay, so let's talk about twinning really fast, right? We're not talking about annealing twins here, okay? Annealing twins in metals happen because of growth accidents, okay? That is not, the structure is the same, right? We still have the same type of mirror plane and stacking sequence faults that we'll talk about later, right? But annealing twins happen during the growth of grains. Deformation twins happen as a result of plastic deformation. They're one way to accommodate a large amount of shear in a crystal, okay? We have a reorientation of the lattice without a change in crystal structure, okay? So imagine we have an atom at the center of each one of these ellipses. Okay, this is an analogy to understand sort of how twinning happens, right? Why we can get this macroscopic sort of shear with all of the atoms moving only a small relative distance. Now imagine each of these ellipses rotating. So instead of their long axis being parallel to this plane, now in this region, we have the short axis is parallel. The neighborhood hasn't changed, right? The relative position of the atoms has only shifted a small amount next to its neighbor. But overall, we have a very large amount of shear here. We have a large amount of macroscopic deformation. But this atom, right, this one here, in this B plane, it's still surrounded by all of the same neighbors. And its neighborhood still looks exactly the same. It's just been rotated. Right? And so that's how things are accommodated sort of locally, right? So there's a crystallographic theory. So if we assume that a shearing force is applied, right? Slip gives us shear on a plane like this, right? Twins give us shear by rotation. Okay, so we have a shearing force and we get a kink that forms in our crystal. Okay, so there's a very detailed crystallographic theory that in the metallurgy class I talk about in a fair amount of detail. Here I'm not going to go through it in nearly the same amount of detail that I would in metallurgy class, but this is only possible if for this not to change the crystal structure, we have to have essentially 3 lattice vectors that are going to share the same lengths and mutual angles after the shearing. Okay, that probably doesn't make a lot of sense, but I didn't want to change. I didn't want to make too many changes to the slides because I had these and familiar with them, and I was basically just deleting some stuff out. It's a little easier to think about in 2D. I'm not sure what you mean by the same energy or lower. Maybe let me go through this real fast and that might answer your question. So in 2D, let's think about shearing this rectangular prism to this parallelogram. Okay, if we think about have some plane B, here, before we shear it and after we shear it, it's gotten longer, right? This distance is shorter than the final distance, the initial distance. So plane B's gotten longer, plane D's gotten relatively shorter. The angle that plane B makes with this bottom and top face, right, which are two planes that have remained parallel with each other, have changed. Okay? So obviously plane B can't be one of those. A vector in plane B can't be one of those that I talk about, right? But look at plane C, right? It's the same length. It also maintains a stable orientation with respect to this bottom plane and this top plane. Okay? So plane C is the only plane that whose shape was not changed. Right? And so we have here two invariant planes, right? These parallel planes that are planes that are parallel to the shearing force, and one plane that cuts through. Okay, the same concept holds in 3D. It's just a little bit more difficult to visualize. Okay, and so essentially that's the same thing here. We have this twinned region. These top and bottom planes are referred to as our twinning planes, right? And then we have this set of lattice planes that maintains a equal angle with our planes, right? And we call that the plane of shear. In FCC crystals, our twinning plane is the 1-1-1 close packed plane. Our shear direction that lies in this plane of shear here is the 1-1 bar 2 type directions, right? So our slip systems are the 1-1-0 close packed directions on the 1-1-1 plane. Our twinning plane is also the 1-1-1 plane, but the 1-1 bar 2 direction, right? And so if we see what this right, we see that each atom, this relative atom here, change here, this has only moved a small difference, but again, we have a large amount of displacement out here. Okay. So if we set it up so our two twin planes are parallel to each other, in this configuration, it's easy to see that our twin planes are actually crystallographic mirror planes. Okay, the two lattices match at our twin interface here, and we have a mirror symmetry across our twin plane. Okay, so when you look at it this way, it actually becomes fairly easy to see that this twin interface is actually a very special type of grain boundary that has a high degree of symmetry. This has a much lower grain boundary lower energy than a regular incoherent grain boundary. But it also is related to the stacking sequence of atoms. right? So in FCC, the stacking sequence of close packed planes is A, B, C, A, B, C, A, B, C, right? Where, of course, that, right, if we think about the number of individual holes in a close packed structure where we can set things, we have two possible arrangements of how close packed planes can be arranged on top of each other, right? For twinning, when we have a twin, we have A, B, C, A, and now this twin plane acts as a mirror plane. So if this is C, this is A, this is back to C again, right? So a twin interface is a stacking fault, right? It also has a very particular relationship on the close packed planes. In FCC, right? Here's my cube. What's the defining symmetry for FCC for cubic crystals? Right? It's 120-degree rotation about the 111 crystallographic axis. Right? So if I start here and I rotate 120 degrees, 120, 120, I'm back to green, right? So that's the defining symmetry for cubic crystals, right? 100, this cube's too loose, right? So 120, 120, back to green, 120, right? Okay. A twin is 60 degrees about the 111 axis, right? So that's the crystallographic relationship between twins, cubic twins, right? And if you play with it, you can sort of maybe visualize that that actually is a mirror plane or a mirror symmetry, right? If I'm actually halfway between two equivalent crystallographic states, right? I now have a stacking defect on the 111 plane and a mirror on that 111 plane. Okay. Twinning, the act of forming these is actually a three-step process. Okay. We have to nucleate the twins. These twins, deformation twins, will tend to nucleate at the grain boundary. So we have to make a little nucleus of the correct orientation. How this happens, there is really an open area, so I don't want to dwell on speculation of twin nucleation. But then the twin essentially propagates across the grain, right? And this happens almost instantaneously, right? This is the shear transformation as we go across this. And when I say instantaneously, I mean instantaneously, right? This happens at the speed of sound in the material, right? So this propagation event happens too quickly to be captured on by recording. There's some beautiful experiments in the electron microscopy where you've got electron cameras that are functioning at thousands of frames per second, right? The 4K camera that we have at CMAS does 4,000 frames a second. And all of the twinning experiments that have been done in situ show no twins, no twins, no twins, no twins. The very next frame, there's the twins, right? So step B happens instantaneously. Yeah, so there's lots of different designs for for in situ mechanical stages, right? But the easiest is if you just have a film, have your thin foil in the TEM, right? And you can apply just a tensile load on it, right? You just have two screws, very, very fine threaded screws that just move your sample apart, right? Now, generally, the threads, right, are too big, right? So you can't do it just a very fine screw, but you can do it just by mechanical reduction, right? Is the easiest way, right? You can also have MEMS systems, piezoelectric systems that grow and contract, right? Which is actually a much easier engineering solution, but a little bit more difficult to visualize, right? Right. And then once we have the twin is there, it grows, right? The actual mechanisms for growth are interesting because it's actually dislocation mediated, right? You run certain partial dislocations across this, and it moves the twin, grows it one layer at a time, but that's really beyond the scope of this class. Really, what I wanted to do is just set up this idea of a shear transformation and how a local change, a local small move, relative change of atomic positions can give you a macroscopically large sort of strain. And this idea of an invariant plane, right? Where we have a plane that doesn't change its angle with respect to the applied force, and it doesn't change its length. All the vectors in this plane remain the same, right? And these are important concepts that go over to martensite, right? So on Monday, we will talk about the formation of martensite and martensite transformations, okay? And this is different in with respect to things that we talked about before, because this is a diffusionless transformation. So what does that mean, right? It means that it won't take place over the same range of compositions that diffusional phase transformations take place, and the driving force is different, right? So there most definitely can be office hours today. I will be happy to be available for anyone who has questions. Right? They're the standard noon, right? At least I think it's noon. I have to check my calendar. But yeah, noon to 1. Yeah, standard time. Right? So have a good Thanksgiving, everybody. Stay safe, stay healthy. Right? Okay, we'll see you on Monday. Enjoy the long weekend.